Okay, so in this video, we'll consider an application of the determinant. And this is called eigenvalues and eigenvectors. Let's consider the premise. We assume we have a square matrix A. So suppose A is an n by n matrix. We assume we have what we'll call our eigenvector. So V will be a n by 1 column matrix. So V consists of n entries, so V1, the first entry, V2, the second entry, up to the nth entry, Vn. So this is a n by 1 matrix. And one other thing, lambda will be our real number. This is the Greek letter L called lambda. And suppose we have the following equality. Suppose that A times V. So we multiply this vector by the matrix A. Because A is an n by n matrix, and the vector is a n by 1 matrix, A times V is defined, and the result will also be a n by 1 column vector. And sometimes, for very special choices of vectors, A times V will simply be a scalar multiple of V. And if this happens, if AV equals lambda V, then we call lambda an eigenvalue of A, and we call V an eigenvector. So they go in pairs, right? For each eigenvalue, you'll have the corresponding eigenvector. One assumption about the eigenvector is it is not the zero-column vector. So at least one of the entries of the vector v is non-zero. So if there exists such a vector with this real number, we have an eigenvalue-eigenvector pair. Why this is kind of interesting? Well, we know that matrix multiplication is rather complicated. And this says for some very special choices of vectors, A times V will simply be a scalar multiple of V. So the action of V, the action of A onto V, actually in this case is trivial. It simply is scalar multiplication. And because on given vectors, the action of multiplying by A, the vector, is trivial, it's just a scalar multiplication of lambda V, we can take advantage of this, and we'll see that in a few examples. Let's consider an example of where we have an explicit eigenvalue and eigenvector V. And then we'll ask in general, how do we find an eigenvalue-eigenvector pair? So here's an example. And we'll take a 2 by 2 matrix. So we'll take A to be the matrix 4, 2, 3, negative 1. And we'll take as our first vector, call this V1, the 2 by 1 vector 2, 1. And we'll take another vector V2, and say the entries of V2 are 1, negative 3. I claim that V1 is an eigenvector of A, and V2 is an eigenvector of A. Let's check. Let's compute A times V, 1 first. So the matrix A is 4, 2, 3, negative 1, times the vector 2, 1. So what do we get? 4 times 2, 8, plus 2, 10. 3 times 2, 6, minus 1, 5. Well, if V really is an eigenvector of A, AV would have to be just a scalar multiple of V. Well, if you look here, both of these are multiples of 5. So if you factor 5, you are left with the vector 2, 1. So look at that. A times V1, so this matrix times the vector 2, 1, ends up being quite simply 5 times the same vector. So this is simply 5 times the vector v1, and so 5 is our eigenvalue. We'll call lambda 1. You see, AV1, the matrix A times the vector 2, 1, is simply 5 times the vector 2, 1. So AV1 is equal to 5 v1. So the eigenvector here is 2, 1, and the corresponding eigenvalue, lambda 1, is 5. So indeed, 5 is an eigenvalue of A, and v1, the vector 2, 1, is an eigenvector. Let's check v2 as well. Let's do A times v2. The matrix A again is 4, 2, 3, negative 1. v2 now is 1, negative 3. So what do we have? 4 minus 6, negative 2, 3, positive 3, positive 6. Well, we can factor a negative 2 from this vector, and we get negative 2 times the vector 1, negative 3. And if you look at this, we multiply the vector 1, negative 3 by A, and the result happens to be negative 2 times the vector 1, negative 3. This is simply negative 2 times the vector v2, and hence the value negative 2 is the corresponding eigenvalue, which we call lambda 2. Right? So A times v2 is just negative 2 times v2. Now the question is, well, how did I come up with these two vectors? Right? Clearly we've checked that they are eigenvectors with eigenvalue 5 for v1 and eigenvalue negative 2 for v2. How do you come up with the eigenvectors and the eigenvalues? Well, let's go back to the equality AV equals lambda v. A times v must equal lambda v, keeping in mind that v must be a non-zero column vector. Well, let's rearrange this. Subtract AV on both sides. Therefore, lambda v minus AV has to be the zero vector. Lambda times v, write v as I. So I here, since A is an n by n matrix, I will be the n by n identity matrix. But v is simply I times v minus AV equals the zero vector. And you see that both are multiplying v. So you can factor v on the right of this product. So if you do factor v, then you're left with the matrix lambda I minus A. And if you look at this now, we have a linear system, right? The matrix of coefficients is the matrix lambda I minus A. The vector v is the vector of unknowns. And this is the constants, the column of constants, which are all zeros. So you see the eigenvalue eigenvector pair must solve the linear system. So if we were to solve for this, well, we would of course construct the augmented matrix. The vector v is the unknown, so we can write its components v1, v2, vn. The matrix of coefficients is lambda I minus A. And the vector of constants is the zero vector. And there you have it. The only problem here is, to find the eigenvector v, you already have to know the eigenvalue. You can't have an unknown floating in your matrix of coefficients. You already have to know the eigenvalue lambda. Okay, but if we know the eigenvalue lambda, then we have this matrix of coefficients. By row reducing and solving, we will get the corresponding eigenvector v. The question is, how do we find the values for lambda? Look at this linear system. The vector v must be a non-zero vector. Well, the vector v, if you set v to be the zero vector, this matrix times the zero vector equals the zero vector. So the zero vector is a solution, and if we are looking for eigenvectors, there must be another solution which is non-zero that solves this linear system. Therefore, this linear system has to have at least two solutions, therefore an infinite number of solutions. But what does this say about this matrix? Because the system has an infinite number of solutions, this matrix cannot be invertible. If this matrix were invertible, you can multiply by the inverse on both sides, and V would automatically be the zero vector. Since we're looking for a non-zero solution, this matrix must be singular. And then you say, well, think of now your determinant. A matrix is invertible if and only if its determinant is not zero. So this matrix will be singular if and only if its determinant is equal to zero. So, to have an eigenvalue for the matrix A, the matrix lambda I minus A must be singular, therefore its determinant has to be equal to the zero real number. And as we'll see in the next video when we consider an example, if the matrix A is an n by n matrix, this will be a polynomial in the variable lambda of degree n. And we give this polynomial a very special name. We call this the characteristic polynomial of A, and we usually denote this by P sub A for polynomial, and is a function of lambda. And that's basically it. This is how you find eigenvalues and eigenvectors. So first, find this polynomial. The roots, the values that will make the equation 0, will be the eigenvalues. And for each eigenvalue, you can plug it in the linear system. And when you solve the linear system, you will find for the eigenvalue a corresponding eigenvector. And as I've said, this is called the characteristic polynomial of A. Before we move on to our example, let's consider a general setup. Suppose we have an n by n matrix. And you'll see that on the problem sheet, we'll only deal with 2 by 2 matrices to simplify the calculations. But what we're going to say now works for any given square matrix as long as we have n distinct eigenvalues. So suppose we have a square matrix. And suppose that we have n distinct eigenvalues. So lambda 1, lambda 2, up to lambda n. Suppose these are distinct eigenvalues. And for each eigenvalue, of course, we find the corresponding eigenvectors. So v1 for lambda 1, v2 for lambda 2, up to Vn for lambda n. Here's the following result that will be at the core of the application of eigenvectors and eigenvalues. We will construct with these two matrices. The first one we call D, and we use D because it will be a diagonal matrix. It will be zeros everywhere except on the main diagonal. So the matrix D will look like this. Lambda 1 on the first entry of the diagonal, then lambda 2, all the way down to lambda n. And every other entry above and below the main diagonal will be 0. So zeros everywhere below the main diagonal, and zeros everywhere above the main diagonal. And this matrix is called a diagonal matrix because of the main diagonal you get all zeros. That's the first matrix we form. Then we form the matrix that we'll call P. And we put the vectors in P's, right? These are column vectors, so they will build the columns of the matrix P. And put them in the same order. So the first column of P will be the eigenvector that corresponds to the first eigenvalue, so it'll be V1. The second column of P will be the second eigenvector, V2, and so on. So if you look at this, D is an n by n matrix, P is an n by n matrix, and then you will want to find the inverse of P, which is also an n by n matrix. And then the question is, well, what do we do with this? Well, and this we will not prove, but you can check, and whenever you have an example, that actually if you compute P inverse times A times P, the end result will be this matrix. Therefore, if you isolate for A, multiply by P on the left to cancel P inverse, so you'll have PD on the left. So then this will be gone. To cancel P on the right, multiply by P inverse from the right. So you have D P inverse, and the P inverse will cancel the P here. So you'll be left with A is PD P inverse. And this will always be true as long as these eigenvalues are distinct and the matrix P is invertible. This will always work. And the question is, well, why is this useful? Well, it's useful because if you look at powers of a diagonal matrix, it's actually very easy to compute. Right? Suppose I look at a 2 by 2 matrix, and it is a diagonal matrix. Suppose I go with 3, 0, 0, 2. This would be our D. Let's start taking powers of D. Well, D squared, D times D. So 3, 0, 0, 2 times 3, 0, 0, 2. If you compute this, what you'll find is this will be 3 squared, 0, 0, 2 squared. If you find the third power of D, so D cubed, this will be D times D squared. So D times D squared, 3 squared, 0, 0, 2 squared. And if you multiply, you'll find this will be 3 cubed, 0, 0, 2 cubed. And in general, you can see where this is going. If you ask, well, given that D is a diagonal matrix, what is D to the nth power for any n? What you get is simply the nth power of the diagonal entries. So 3 to the n, 0, 0, 2 to the n, for any n greater or equal to 1. And that's really the idea. If you have a diagonal matrix, it's very easy to find its powers. You simply raise the diagonal entries to the exponent. And this will be the application we'll consider in our next video. We'll say, well, what if we wanted to find a really high power of a matrix that is not a diagonal matrix? Why would this be nice? Well, let's compute a squared and a cubed and see if we can guess what's going to happen. So we say, well, A, and if you recall, A is PD P inverse. So if we do A squared, this will be P D P inverse, so this is A, times A again, times P D P inverse. But if you notice, the P inverse times P will give you I. This will cancel, and you'll be left with P D D P inverse. This will be P D squared P inverse. So you see that A squared is P D squared P inverse. What about A cubed? Well, it would be A times A squared. A was PD P inverse times A squared P D squared P inverse. Once again, in the middle, P inverse times P is I. This will cancel, and you'll be left with P D D squared is D cubed P inverse. So you see that A cubed is p d cubed p inverse. And you can extend this for a to the fourth, a to the 5, a to the 6, a to any given power. So if you said, well, what's the nth power of a for any n, it will simply be p d to the n p inverse. And think of why this is fantastic. If I give you a matrix that is not diagonal, and I said find, say, the 50th power, you'd have to do a times a times a times a times a times a 50 times. But if you use instead this equality to find the 50th power of a diagonal matrix, you simply take the 50th power of the diagonal entries. So no matter how big n is, this will require absolutely no work, and you'll be left with 1, 2 multiplications. So no matter how large n is, this will always require only 2 multiplications, whereas this will require larger and larger number of multiplications. And this is or at least one of the really neat applications of eigenvalues and eigenvectors. And we'll do this in our next video. We'll consider an actual example where we'll find a formula for the nth power of a matrix with the help of the eigenvectors that will build P and the eigenvalues that will build the matrix D.